Hi everybody, and welcome to our latest LBG medical seminar. Today we have planned to speak to you about 3D printed soft shell TPU devices. Now, this is a new brand we have to offer. We can plan on giving you all the information you require to start ordering and prescribing these orthotics. We will also be mentioning some of the great advantages that we have to offer you compared to some of the other relatively new printer competitors have on the market. In today's agenda, we have two great speakers that we're presenting our 3D printed product for you. Apologies. In today's agenda, two presenters. I'm Brett Rudd. I'm the technical manager for LBG. If some of you guys are not aware of me by now, I've been working with LBG for the last 2+ years or so. I have 15 years of experience working in the digital side of orthotic manufacturing with CAD/CAM technology. We also have here today Chris Lawrie. Chris is representing Fit 360 and has been driving the development of CAD/CAM software applications within our business. Chris will be giving us a great in-depth knowledge of printing and its application. I'm sure most of you today are now fairly familiar with printing, but for those of you who may not, I'm sure you'll be ready to go after today. We'll also be introducing Ian Drakard. Ian is the Managing Director from Angel Podiatry, who works with a great team of podiatrists there. Okay, so Ian also shares a great deal of knowledge with the digital design orthotics and will be sharing a case study that illustrates and benefits the successful solution that the TPU tech have delivered to a patient he's personally prescribed. So I hope you can all give a warm welcome to Ian and Chris also. And today we will also wrap up today with a Q&A session where we aim to answer any of the questions you may have. Hopefully you guys will have plenty to ask the team. So let's begin then. So why use TPU prints? Okay, what are the advantages to you guys? How is it going to help you, and what's going to be a likely consideration when prescribing orthotics? Most of you are aware of our combination devices by now, which we produce with traditional manufacturing methods. Okay, so we call this subtractive manufacture. And as you can see from the image there, we're using CNC technology to cut into solid blocks of material with cutting tools, opposed to 3D printing, where we use a manufacturing technique called additive manufacture. So no blocks of materials or industrial 3-axis machines or any of such required for that process. So what's the benefits? Okay, so we are removing the boundaries of what we can produce and give to you as practitioners. Okay, although subtractive manufacturing has been a great solution, it does come with its limitations as to what we can produce with traditional methods. Currently, you can see here we use a knife press, and we've made these to spec of what we offer on our order forms. Now, these do have a beneficial place. You can select, for instance, the forefoot of an orthotic to be a low density and a medium density for the midfoot. Okay, so that's great. This may suit the requirements of your assessment, but these are limited. We can only get these knives made in a few options. You'll be aware from the prescription forms that these are very basic and we can't really adjust those. With 3D printing, we've completely removed this boundary and the limitations that come with it. So now we can manufacture any region or orthotic or zone to any spec you require. So your options now, guys, are endless. So let's break this all down for you. Okay, so for example, your patient's requiring a high degree of control, but the device has to be comforting. Like I say, a low density, soft device is needed. So we can add a curved skive, let's say a medium or high density, but only in that region area. Now, the curbing can be made in this select density while maintaining the lower density comfort zones around the rest of the orthotic. So this is just one very, very basic example of what we can apply, opposed to a combination subtractive approach that you're having to make compromises with usually. Now, we can have any zone or any area to meet your requirements. So these can be on a plane system. So it might be horizontal slices, a vertical slice can be made. We can adjust the transitions with these. Okay, so we can adjust the degrees, and these can be placed from one zone to another. Okay, so we can have multi-zones, one area to another. So we'll look at this further, and I'll show you, and we can interact with the zones with a video demo later. So going on forward, I'd like to introduce you again to Chris Lawrie, and Chris Lawrie will be able to give you some background information with regards to TPU. Over to you, Chris.
Thanks, Brett. Hi, yeah, my name's Chris Lawrie. I'm from a company called Fit360. We're not a huge company, so I thought I'd introduce myself just in case you've never heard of us before. And then I'm going to talk a little bit about why we as a company have developed this technology that LBG are now using. Now, before we start, it just occurred to me at the beginning, you're the first people to ever see this. What we're going to show you today is very new and very unique, not just to LBG, but also to the community that we all work in. So I hope that comes across in the presentations. So who are we? We're a software company, and we make software for designing insoles, whether they are full-length EVA devices to be milled, three-quarter length devices to be 3D printed in nylons, or whether it's a mold. And how we make it, which we'll go into more detail in a moment, is either going to be subtractively or additively, cutting material away or adding material to make the part. And we'll come into that in a bit. So that's what we do as a company. Our software has loads of clinical tools in it for creating fit and function in different styles of devices I mentioned. So, and we can also decide how it's going to be made as well. We can generate the toolpaths and generate the parts. We're also, and this is a little bit of marketing on us, is we're fully digital. We have no physical thing in our business. The team, and some of them are on this call, are geographically dispersed. We work through the cloud. We deliver our software through the cloud. We also train people and look after them through online systems. And as a result, we are green. We are actually carbon positive. We plant trees for every demo we do for the energy part of it, and as a result, we're proud to say that we contribute rather than positively or rather than negatively to the carbon footprint. We may be small, but we do quite a lot. We're well distributed around the world: Australia, Canada, USA, UK, Spain, Europe. I mean, anywhere you can imagine, we have customers now. And they between them, this community, are making 1 million pairs a year of insoles, whether they're printed, milled, or whatever. And that's about 80,000 a month, of which 17,000 of them a month are 3D printed, mainly at the moment through rigid material. And that leads us nicely onto the story of soft material, which we're talking about today. So if you look at the whole spectrum of what's possible, whether it's a rigid device, a soft EVA-like device, or whether it's a mold, there are two ways of making it. One is by 3D printing, one is by milling. By milling, you can mill in foam or wood to make a mold for carbon fiber layer, or you can mill the EVA directly or polypropylene directly. So what does that look like? So if you haven't seen it before, subtractive machining looks like this, where you have a block of material and you cut the part out of it that you want. Fast, reliable, repeatable, and millions of people are doing this all over the world, and it's a very good process. The challenge comes, though, when you want to get rid of what's left. So if you cut something out and you've got this high value product in the middle, you've got to get rid of the waste. And this is a photograph of a company in New York that we work with, and that's their material coming in on the right, and that's the material going out on the left. And 80 to 90% of it's going in the bin. Now, companies like LBG Medical are, really into the idea of being responsible with the environment. So that's one of the reasons why they're looking at this TPU solution. So going back to our diagram, We can print in nylon materials, rigid parts. I don't know if I've got one here I can wave in front of the camera. So that type of device can be 3D printed in a powder system. But we're going to look at the the TPU approach, which is soft material now. Now, there are two ways of printing TPU. One of them is area-based, where a bit like screen printing, a system is curing a layer and then the bed drops down and it cures the next layer, etc., etc. And on the right-hand side, you have the extrusion method, which instead of being area-based, it's like a CNC machine. Instead of cutting, it's laying material down like toothpaste. So they're very similar in the sense that the material they can generate is TPU, but the manufacturing method on the left is far more challenging than the manufacturing method on the right, that they have benefits over each other. But at the moment with TPU, the cost of powder printing in processing is really high, whereas it is much more affordable on the FDM extrusion route. So going in a bit more detail here, the powder approach, in our software, we can produce a design, produce a solid model that comes out that has all of the geometries built into it that we're going to use for creating variable density, or variable stiffness rather. And then you would go into a slicing software that would do an area-based cure of that by dropping down in Z, and that slicing software would send the data to the machine and you get your part off. Huge amounts of processing of getting the powder out of the gaps afterwards, because it's the powder that is supporting the part during the job. With the extrusion method, FDM or FFF, you've got the same model, but what we do is we identify zones in the design process that have got manufacturing knowledge built into them that we then send to our own slicer that generates really optimal moves for the machine. We don't know anything about printing a car. We don't know anything about printing parts for day-to-day use. We only know about printing and creating a slicer for insoles, which gives us the advantage of optimizing the process. And that goes to a machine which is much more affordable than the powder system to give you a result like the ones that Brett was showing you. So how can you create variable stiffness from a single material? Surely, if you have a material like we have our EVA blocks, shore hardness 50, no matter what you do, it's always shore hardness 50. But the whole principle of infill we're going to show you now is based on the fact that you can create springs. So if you took steel, you wouldn't put steel in a car for a shock absorber unless you coiled it and turned it into a spring. So the same material that in its normal form is not very flexible at all becomes flexible. And we can do exactly the same thing here with either powder or the TPU material, because those springs that we put in, the internal structures, change the stiffness in that region and change then the effective shore hardness of the part. And that's how it's being done. So let's take a closer look at some of the benefits. Now, Brett touched on some of this already, but I'm just going to go over it again, is that when you're dealing with variable springs in the same material, and I am simplifying this a bit because there are actually things we can do with the material during printing to change its properties as well, but this is just a way of getting it across at the moment, is you can have a hard region, a medium region, and a soft region in the insole, as you would be familiar with in EVA, but you can also have very rigid regions in there as well, all combined into one build. So you get multiple density volumes. They are not layers that are exposed, they are integral into the insole itself. So if we were looking at the EVA approach, you could have a medium perhaps and a rigid zone that you expose when you're machining, but it limits exactly what you can do. But when you go to the printing method, we can control exactly where those zones are and how they perform for the patient. And this is about clinical outcome. And as I said before, we can change the flow and the material temperature in here as well, because we own the slicer software. We're able to control it in a way that makes it more advantageous for the user. So for example, in the hard area, we might be using one temperature, and in the soft area, another temperature that creates air into the material that will create less stiffness as well. The most important thing to me, and I talk about 3D printing a lot, it's an evolution, not a revolution. The idea that you would create the craziest, coolest insole in the world with all sorts of beautiful patterns in it for the sake of it is something we need to avoid. We need to move the clinics and the patients over in a controlled way using logical steps, which is just to have more density variation in the part. So looking at that volumetric stiffness, inside, if we were to cut through the model, if you were cutting proximal to distal down the middle, you would actually see volumetric changes in the stiffness to achieve a better result. So how does that convert to clinical benefit? It means, and you're going to see Brett doing this live in a moment, it allows you to create zones in the part that you store as prescriptive ideas. So you might have something that has a soft midfoot and a super soft forefoot and a hard area in the heel. And these zones are stored so that when Brett's designing, he can select what he wants from the prescription forms you guys are filling in order to create the part that he wants. And it's totally flexible what you can do. And we're working with LBG to identify what is best for them to store. And what you see is what you get. It's very simple graphically on the left, but if you apply that zone, there's manufacturing knowledge embedded inside it that tells the printer how to make that region. So it's very straightforward from the modeling through to the manufacturing part of it. And I think the bit I've alluded to a couple of times, and this is my final slide, the bit I've alluded to a couple of times is that the slicer integration is what makes this work. Because what we're doing is we're in the design process, we're saying, actually, I need this met dome to be an effective, stiffness of X. And I'm going to do that in design, and it carries the manufacturing knowledge through to the end and prints it that way to give you that result. That's what the integrated slicer gives us. And I think ultimately it gives the optimal clinical design. The manufacturing process is now doing less to constrain you than it did before, so that you can get those results you want for the patient. And also, the variable shore is no longer limited by the material. And I put within reason. You go crazy with this, it'll bite you. You'll end up with something, if you have small zones and variations in it, that will just give you something that looks okay, but doesn't really perform as you want. So it is an evolution, not a revolution. And this is my segue into Ian's presentation, hybrid designs are possible. You can integrate skives, stiff features into the same design as a soft device. And also you can put grinding and trimming features in there. So in that example there, you can see on the first image, you can see that there is a black forefoot region, and that's designed so that you can optimize it in front of the patient to fit their shoe. So you could do that as well. At that point, I'm going to hand you over to the really interesting bit, which is how does this work clinically? So over to you, Ian.
Thanks, Chris. That was a fantastic overview. So as Brett mentioned, I'm a clinician, but I've also had 15 years of experience with kind of digital applications. So what I want to kind of show you is a couple of the kind of clinical applications where we can kind of see how this interacts with our kind of patients in the real world. So the main way, not the only way, but the main way that orthoses work is going to be by changing the reaction force between the foot and the ground. So obviously, traditionally, we've incorporated changes to the geometry of the device into our design. We've started from a cast or a scan, and we've designed the device around that and then made modifications. So with that, we've selected the material to then alter the load deformation characteristics, and those two things obviously interact. So obviously, if we change the kind of arch height, that will also alter the load deformation. So the geometry and the material will have this interaction. What's kind of fantastic with the option of 3D printing, and especially with the FDM method that we're kind of using for these soft shell devices, is that we can control the material structure and some of the material properties as we print it within a single material. So that gives us some distinct advantages which we can start to take advantage of clinically. So kind of touching on what sort of Chris has just mentioned, we can have zones of different structure and density within the device. But we can also have layers of variable structure and density. So we can start to think about how we might use different material combinations traditionally and start to build all of that into a single device. So where we'd traditionally use maybe separate mid layers on top of things, well, actually, we can produce a layer through the device in the middle or on the top, which will reproduce some of those material characteristics we traditionally get by layering up different materials. One of the other big advantages is we're not limited by the material proportions in the same way, where the limiting factor is going to be the size of the printer we're printing on. So where traditionally with, say, subtractive manufacture, we'd be limited by the kind of block size. We can, so I've got an insole here in front of me that has for a kind of quite a cavoid foot, and we've got about a 55 mil arch depth. Now that's very hard to reproduce in subtractive manufacture, and normally you'd achieve that either by layering up blocks of material to get that, and therefore you get material defects within it that can affect the longevity of the device, or you'd have to resort to kind of vacuum forming over a very, very deep positive cast. So there might be cost and time implications to producing very deep or very long devices, but it's possible. And one of the big things which we might sort of touch on again is the repeatability of prescription. Because we're designing in a lot of the both the geometry and the shape of the device, but also the density of the device. When we come to reproduce that, if we're producing it on the same printer with the same code, we know we're going to get an identical device. So if that patient wants something that's worked well for them again in 6 weeks or 6 months or 6 years, that is going to come back as we expected it every time. So we're going to look at a sort of case study where we've been able to use a lot of the advantages. So this was a gentleman who was a type 2 diabetic, and on his left side he'd actually had a transtibial amputation and used a prosthetic. The right side is the one we're interested in. So we'd actually had a transmetatarsal amputation, and we needed to produce a device that stopped any further problems into the future. So our kind of main objectives, so we took a scan of the side, and the single biggest objectives were to prevent areas where we might get excess pressure or shear stress, because the last thing we wanted was any further ulcerations which ended up in progressive problems. We also had an issue with lateral instability. So it was very hard on that affected side for him to not end up sort of tipping over. So he's also then using a stick as he felt he was going to go over on his ankle all the time. And we also needed to provide a slight raise to adapt to the height for his left side prosthetic that had been given. So we'd made a fairly successful device using subtractive manufacture. So we made this out of a milled polyurethane with just a thin EVA cover. And it had worked pretty well, but there were some limitations to the device. So the block size out of the polyurethane we'd used wasn't sufficient to allow for the additional heel raise that he required. So we then needed to add that on after the fact. The other slight issue was because of the limitation of a 3-axis milling machine and the milling angle, the toe block had to be vertical at most. It couldn't be concave, and what that does is it limits the contact area with the foot. And the bigger the contact area we can get, the better, because that's going to spread and redistribute the pressure to where we want it. And finally, it needed hand finishing in a polyurethane material to produce the under bevel and the arch contours. And therefore, if he needs it again, it's going to be dependent on the kind of skill of the technician to kind of reproduce that each time it's made. So some of the advantages we're able to introduce through a 3D printing and FDM process are the toe block concavity could be produced because we're not limited by that kind of milling angle, and that allows for greater contact area and a better pressure distribution. We're able to put in an integral heel raised to the height we want, so there's no further additions that we need to put in. And then in addition to that, we could build in not just a lateral heel skive to promote the lateral stability, but we could also integrate a different density zone, improving the stability on that side. When we're working with different density zones, the other thing we added in was actually relatively thin but solid arch support. And the reason we did that is because I want this device to be able to be moved from shoe to shoe with limited interaction with the shoe upper. But I want it to also be stable and give the same level of support in each shoe. So here we are where it's in production. And there's the finished device from the design, and that has allowed us to kind of get what will turn a good result and turn that into an even better result for that patient. So that's a kind of example, a sort of fairly extreme example of what we can do with it, but a kind of everyday example that I think we'll all come across is where we're dealing with a foot that's developing problems because we've got a slight medial deviation in the subtalar joint axis. So here's Kevin Kirby's lovely illustrations denoting our kind of axial location. And if we palpate and get the transverse plane approximation of that axis, we can give some indication of what we need to reproduce into a device. So with this patient, what they were presenting with is a second metatarsal overload. So they were getting plantar plate issues, which was also causing apical lesions where the digits were retracting. But what was really driving it all is the posterior tibial tendon issues and gradual progression that they were getting. So although what was bringing them in was the kind of symptoms they were getting at the forefoot, what we really need with this device is a combination of rear foot control with that as well. And what I want to kind of show with this is how the material alterations we can make in different zones gives us another option that is going to be suitable for some sort of patients where we need a combination. So if we look at where we want to focus our reaction force on the device, we can adjust the device along the subtalar joint axis line. So if we make an approximation that with the patient, we can then actually design a device that is zoned in a similar way. So when we were translating that to this patient, we incorporated a lot of the design features you tend to expect with a posterior tibial tendon function device. So we could incorporate a rear foot posting and medial skive. We could have a slightly deeper medial flange, a deeper heel cup. We could actually design in some of our accommodations. In this case, we didn't need any particular accommodations for navicular or first mate cuneiform, but we did want some for the forefoot. So we incorporated a met pad, and we actually incorporated a toe prop to help with the apical lesions, as that's something the patient was using regularly anyway. But in addition to that, we could have a zone of density where we could stiffen the heel cup, and we could stiffen the arch and stiffen the medial flange to give the control that you'd normally associate with a much higher density material or shell type device. So here's that as it goes through production, and you can see there the zone where we've kind of stiffened through to provide that extra very, very high density in this case. And there's the finished device, which has just got a light cover on. So hopefully that's an example which is going to give you some data or be applicable on your day-to-day and sort of week-to-week caseload, where you can see how we can combine different features and different densities and put it all into a device with pretty much a single material. So obviously I'll take any questions at the end, but if I can hand over to Brett now, I think he'd like to take you through some of the design.
Okay, thanks, Ian. That was an absolutely brilliant talk there, showing us some of the clinical evidence and how we can really apply some of these advantages of this product. So I'd just like to show you now some of the basic designs, how we actually apply these within 360 within the software. Now today we are just going to do a couple of basics. So obviously we've seen how much we can interact with these TPU devices. We consider there's no limitations with them really, how much we can apply. But let's just give you a few examples. So following on from Ian's research there, so we can see here this one example for a curved medial Kirby skive. Okay, so you can see we can simply sketch this area. And now we have what we call modifiers that we've touched on. Okay, now we have a range of options. So we can go from filling in with a gyroid, or we have a raster fill, which we can see there. So we have multiple options. One second. Yeah. Left one. Okay, guys, sorry about that. So yeah, sorry, just jumping back into my screen there. Okay, so again, just to quickly just recap over we're just speaking about. So again, with these surface modifications, as you can see here, we've got the Kirby. So within our modifiers, okay, we have a range of options available to us now. So we've got our presets. Okay, so we can go from 1 to 7. Okay, so you can see how this is going to build. Okay, so the density here is obviously we're building up a high density there, and then we can go through a range, okay, on whatever the specification is that you require. And a nice little neat tool that we have here, okay, we can see where we can change the angle and inclination, so how this transits within the other regions and zones. Okay, so it doesn't necessarily have to be vertical. Okay, so we can change the angles and the way this interacts with the device. Okay, so and apply that. Now, if say we wanted to add, let's just show you another part, for example. So this particular device requires an integrated met dome. Okay, so we're not going to apply this traditional methods. We're going to build this into the print. Okay, so I can actually make this any size. I'll select any regions I want. Okay, and as you can see, okay, back into this zone here again, and the same kind of applies. Okay, so we have our taper angles, and you can see how this will interact. Right. So following on from our video there, we'd just like to touch on prescription forms. Okay, so we've tried to keep in reflection of our previous forms rather than being too overwhelming. And I'm sure this webinar now will have put you in control of the requests and the options that you'd like to add. Okay, so if I quickly just show you order form. Okay, right, so as you can see, it's very similar to what you guys are used to using. Okay, we've tried to keep a reflection with the rest of our order forms that are available to you in regards to our traditional orthotics vacuum form processes. So we have all of our details, standard details. Cast spec is all there related again to the previous. Now, the important thing for this product, so our TPU, okay, we have included some of our combination options that were previously are previously available to you. Okay, so we can still use those. We can still use those, and we can give you them obviously with the advantages now of TPU. So the better technology that's involved with these, okay, you're going to get a slightly better product with the combination device now. And we also have what we call our custom combination now, which is for you guys. Now, obviously, you can draw in your options, okay, here. Now, you can have, obviously, however you want your design to go in there. Okay, you can simply add this onto your additional information here. You can just simply sketch that in. Any thoughts or any requests that you require, just let us know, and obviously we can see if we can meet those. We should be able to meet those for you. And secondly, which is a nice thing that obviously we've added into here, is integrated printer edition. Okay, so these paddings that have been on our previous order forms, so you can see we have obviously traditional, so a pour on an EVA can still be added as previously, but with our new TPU, okay, so we can start adding some of these regions in with the TPU and integrate it into the shell. Okay, so we can build these options in for you.